Hi, I am Prashant, and today I am going to do a presentation on Cayley-Hamilton theorem for roboticists. Abstract. The Cayley-Hamilton theorem is an important theorem of linear algebra which is well known and used in system theory. But unfortunately, this powerful result is practically never used in robotics, even though it is of extreme relevance. This presentation is a review of the use of this method for the calculation of general matrix functions, which are very common in robotics. It will be shown how any analytical matrix function like exponential, logarithm, and more complicated expressions in robotics can be easily and analytically calculated in an explicit form. Introduction. The Cayley-Hamilton theorem is a well-known theorem in control theory which is used among others to study the Jordan form of linear system. This theorem states that a matrix A satisfies its own characteristic equation. If the characteristic equation does have roots with multiplicity higher than 1, there may also exist a smaller polynomial called minimal polynomial with the same roots but with lower multiplicity, which is also satisfied by the matrix itself. So, now let's talk about the mathematicians who discovered Cayley-Hamilton theorem. Arthur Cayley. Arthur Cayley was a British scholar who helped in founding the British School of Pure Mathematics. Sir William Hamilton. He was a British Irish mathematician as well as a physicist and astronomer. The Cayley-Hamilton theorem allows us to compute functions of matrices like the matrix exponent or matrix logarithm in a straightforward and uniform way by making use of the fact that a matrix taken to a certain power can be expressed as sum of lower power of the original matrix. The Cayley-Hamilton theorem and its associated corollaries have been known for a long time, and they are commonly used in fields of linear algebra and system theory. On the other hand, to the author's knowledge, they are not commonly used in the field of robotics, despite several powerful applications described in this article. Robotics make elaborate use of matrix functions. For example, 3 by 3 rotation matrices are used to describe rigid body orientations, and 4 by 4 homogeneous transformation matrices are used to describe rigid body motions. So now let's move on to matrix functions. Here let's start by stating the Cayley-Hamilton theorem. Theorem 1. Cayley-Hamilton. Let A be a square n by n matrix. Its characteristic equation is det of A minus lambda I is equal to 0. This is a polynomial equation of degree n. Lambda power n plus A n minus 1, lambda power n minus 1 plus so on up to lambda into A1 plus A0 is equal to 0. The roots lambda I of characteristic equation are the eigenvalues of A. Then the matrix satisfies its own characteristic equation an plus an minus 1 into a power of n minus 1 plus so on up to a1a plus a naught I, where capital A is the matrix and I is the identity matrix. This proves follows the definition of eigenvalue lambda mu is equal to a nu, where nu is an eigenvector of A. Eigenvectors are characterized by a direction only and are independent on their length. If nu is an eigenvector and then also lambda nu is an eigenvector, and therefore a square nu is equal to lambda square nu and so on. This theorem has two important corollaries. Corollary 1. Matrix polynomial. Any matrix polynomial in A of degree greater than n can be written as matrix polynomial of degree less than n. This is because the higher powers of A can be written as the sum of lower powers, with a power of n is equal to minus a power of n minus 1 into capital A power of n minus 1 minus so on up to minus a1 into capital A minus a naught into I, where capital A is the matrix and I is identity matrix. Corollary to matrix inverse. The inverse of non-singular matrix can be written as a matrix polynomial of degree less than n. A inverse is equal to minus 1 by a naught into a power of n minus 1 minus a n minus 1 by a naught into a power of n minus 2 minus so on up to minus a1 by a naught into I. Theorem 2. Matrix function. Any analytic scalar function of a scalar argument x can be extended to a square matrix function f of a of a square matrix argument A. With corollary 1, the matrix function f of a can be written as a polynomial p of a of degree less than n. F of a is equal to p of a is equal to p of n minus 1 into a of n minus 1 plus so on up to p of 1a plus p naught I, where a is matrix and I is identity matrix. The coefficients of p of a can be found by evaluating f of x at the eigenvalues of a. Eigenvalues of rotations and motions. In this section, the eigenvalues of rotations and motions are computed. These eigenvalues are used in the computation of matrix functions. Theorem 3. Eigenvalues. Let A and B be square matrix with B is equal to exponential of A. Then if lambda is an eigenvalue of A, then nu is exponential of lambda is an eigenvalue of B. The characteristic equation is that of omega minus lambda I is equal to minus lambda cube minus lambda omega 1 square minus lambda omega 2 square minus lambda omega 3 square. That is equal to lambda of lambda minus I omega into lambda of lambda plus I omega, that is equal to 0, with omega is equal to root over omega 1 square plus omega 2 square plus omega 3 square. So its eigenvalues are lambda 1 is equal to 0, lambda 2 is equal to I omega, and lambda 3 is equal to minus I omega. The eigenvalues of R follow the theorem 3. They are lambda 1 is equal to exponential of 0, that is equal to 1. Lambda 2 is equal to exponential of I omega, and lambda 3 is equal to exponential of minus I omega. A motion, rotational and translational, can be represented as an element of Lie group SE of 3 with a 4 by 4 homogeneous transformation matrix. H is equal to RP01, where rotational part R is a 3 by 3 orthonormal rotation matrix, and the translational part P is a position 3 vector. Alternatively, it can be represented as an element of the corresponding Lie algebra SE of 3 with a 4 by 4 matrix, where the rotational part is a 3 by 3 antisymmetric matrix and the translational part is a 3 vector. T is commonly known as a twist. H and T are related by the matrix function H is equal to exponential of T and T is equal to ln of H. The characteristic equation of T is that of T minus lambda I is equal to minus lambda power 4 minus lambda square omega 1 square minus lambda 2 omega 2 square minus lambda 2 omega 3 square, that is equal to lambda square into lambda minus I omega into lambda plus I omega, that is equal to 0. So its eigenvalues are lambda 1 is equal to lambda 2 is equal to 0, lambda 3 is equal to I omega, and lambda 4 is equal to minus I omega. Note that they do not depend on elements of nu. The eigenvalues of H is equal to exponential of T follow from theorem 3. They are lambda 1 is equal to lambda 2 is equal to exponential of 0 that is equal to 1. Lambda 3 is equal to exponential of I omega and lambda 4 is equal to exponential of minus I omega. B. Exponential map. In this matrix, exponentials for rotations and motions are computed using the eigenvalues from previous section. First, the exponential map for rotations r is equal to exponential of omega is computed. Omega has a eigenvalues lambda 1 is equal to 0, lambda 2 is equal to I omega and lambda 3 is equal to minus I omega. Using theorem 2, we get the following matrix. Upon solving the previous matrix, we yield three independent equations which can be solved upon to get three coefficients P0, P1, P2, where P0 is equal to 1, P1 is equal to sin omega by omega, P2 is equal to 1 minus cos omega by omega square. The resulting polynomial R is 1 minus cos omega by omega square into omega 2 plus sin omega by omega into omega plus I. This result is the same as the well-known Rodriguez formula because the matrix exponential for rotations over an angle of 2 pi more or less yields the same rotation matrix. R is equal to exponential of omega is not injective, that is, it is not 1 to 1. Now the exponential map for motions h is equal to exponential of t is computed. T has eigenvalues lambda 1 is equal to lambda 2 is equal to 0, lambda 3 is equal to I omega and lambda 4 is equal to minus I omega. Evaluating f of lambda I is equal to p of lambda I. Because eigenvalue lambda 1 is equal to lambda 2 is equal to 0 has multiplicity m is equal to 2. Here also the first derivative d of f by d of x into lambda 1 is equal to d of p into d of x into lambda 1 must be evaluated. So consider the following matrix. Here, since the original matrix is real and the image matrix is real, the coefficients must also be real. Here this fact is used to find the coefficients. P0 is equal to 1, P0 is P1 is equal to 1, P2 is equal to 1 minus cos omega by omega square, P3 is equal to omega minus sin omega by omega cube. So the resulting polynomial is h is equal to exponential of t, that is equal to omega minus sin omega by omega cube into t cube plus 1 minus cos omega by omega square t square plus t plus I. This implementation of exponential map for motions can be checked against other implementations from the literature. Inverse of exponential map. In this section, the inverse of the exponential map or matrix logarithms for rotation and motions are computed. First, the inverse of exponential map for rotations is computed. R has eigenvalues lambda 1 is equal to 1, lambda 2 is equal to exponential of I omega and lambda 3 is equal to exponential of minus I omega. Evaluating f of lambda I is equal to p of lambda I, we get the following matrix equation. So solving the matrix equation, we get the coefficients P0 is equal to minus omega cos 2 omega plus 1 by 2 sin omega, P1 is equal to omega sin omega by cos omega minus 1, P2 is equal to minus omega by 2 sin omega. The resulting polynomial is ln of r, that is equal to minus omega by 2 sin omega r square plus omega sin omega by cos omega minus 1 r plus minus omega into cos of 2 cos omega plus 1 by 2 sin omega into I. This implementation of inverse of exponential map for rotations can be checked against other implementations from literature because the matrix logarithm for rotational always yields rotations with an angle omega less than pi is not surjective, it is not 1 to 1. The singular in omega is equal to 0 and omega is equal to pi. For omega is equal to 0, this is because the rotation axis is not well defined for rotation angle of 0. For omega is equal to pi, this is because there are two possibilities for sign of rotation, clockwise or anti-clockwise. Now the inverse of exponential maps for motions t is equal to ln of h is computed. H has eigenvalues lambda 1 is equal to lambda 2 is equal to 1, and lambda 3 is equal to exponential of I omega, and lambda 4 is equal to exponential of minus I omega. Evaluating f of lambda I is equal to p of lambda I, because eigenvalue lambda 1 is equal to lambda 2 is equal to 1 has multiplicity m is equal to 2. Here also the first derivative must also be evaluated, and we get the following. And considering the following matrix equation and solving it for coefficients, we get p naught is equal to 2 omega cos square omega minus sin omega minus omega by 2 sin omega into 1 minus cos omega, and so on. Now let's move on to the next part, derivative of exponential map. Let s is equal to dh by dt into h inverse and t is equal to ln of h. Note that both s and t are both twists, but t has the dimension of meters and radius and is a position, while s has the radius of meters and radians per second and is a velocity. The relation between d capital T by d small t and s is given by derivative of exponential map. This relation is very useful in modeling and simulation of spatial springs in exponential coordinates. So d capital T by d small t is equal to d by d small t of ln h, that is equal to ad of capital T by exponential of ad of capital T minus 1 s, that is equal to j of t into s. Here ad of t is an adjoint representation of Lie algebra of t, and exponential of ad of t is equal to ad of h is adjoint representation of Lie group of h. The matrix division can be written in way because the numerator and denominator commute, so left and right division are the same. This is a good example of matrix function that can be computed with Cayley-Hamilton that could otherwise not easily be computed. So for example, for rotations, consider the following matrix. So here solving for the matrix equation, we get coefficients p naught is equal to 1, p1 is equal to minus 1 by 2, p2 is equal to minus omega cos omega plus 2 sin omega minus omega by 2 omega square sin omega. But for motions, consider the following matrix functions with f3, f4, f5, f6 and so on. Now solving this for coefficients, we get p naught is equal to 1, p1 is equal to minus 1 by 2, p2 is equal to 3 omega sin omega plus 8 cos omega minus 8 plus omega square by 4 of 4 into cos omega minus 1 into omega square. P3 is equal to 0, p4 is equal to 4 cos omega plus omega sin omega minus 4 plus omega square by 4 omega per 4 into cos omega minus 1, and p5 is equal to 0. So in conclusion, in this PPT, the use of Cayley-Hamilton theorem for roboticists have been explained. The Cayley-Hamilton theorem allows to any analytical scalar functions to a matrix functions and to compute these matrix functions in a straightforward way. Robotics can make extensive use of exponential map or matrix exponent and the inverse of exponential map or matrix logarithm. Thank you.